Unit 2, Chapter 8, Thermochemistry. Please turn your notes to page 2 of your thermochemistry unit packet. We're going to begin by copying down some definitions. Pause as needed to fill in your definitions. Energy is the capacity to do work. Okay, we're going to know that energy is going to be a capital E, work is going to be a lowercase w. Two forms of energy we're going to look at here: potential energy, energy due to position, and kinetic energy, energy due to the motion of an object. So these two terms, potential and kinetic energy, you will have or have studied them in physics, looking at thermodynamics. So kinetic energy is equal to 1/2 mass times velocity squared. So we're not going to get into the mathematical pieces of this. We're going to look at the chemistry side of thermochemistry or thermodynamics. Heat. Please copy the definitions here into your notes on page 2. Please also make sure you add the fact that you know heat's chemical symbol, heat's symbol, okay, our variable is Q. So whenever I see Q in an algebraic equation, Q represents heat. And heat is the form of energy that transfers from a body at higher temperature to one at lower temperature. Work, it's going to have a lowercase w equals capital F times lowercase d. Work is equal to force times distance. So work is force acting over a distance, and thermochemistry is the study of heat flow for chemical reactions, and that's what we're going to look at in this unit. Please make sure you include the pieces in red on the screen in your notes. All right. So a couple of things we're going to add to systems and surroundings. This is not the only piece you're going to add there in the middle of page 2, so leave some space. First, just a quick sort of reference to what a system and what a surrounding is. System, part of the universe in which attention is given. Surrounding is the rest of the universe. Now that seems very vague, so let's get into a little bit more details when we're talking about looking at chemistry. So in a chemical reaction, the system is the reactants and the products. The surroundings are the vessel the reaction takes place in, so the test tube, the beaker, the flask, a crucible, whatever it might be, the air that surrounds that, or other material in thermal contact with the reaction systems. All right, so continuing on now. This is an example of a very simple thing, a very simple concept of boiling water. So our surroundings would be the beaker, the wire gauze, the ring stand, the heat source, the stuff inside the container, what's going inside the container, in this case water, is a system. Perhaps we don't have a heat source here, and maybe instead we're reacting magnesium chloride with silver nitrate. And then we would see what we got with that reaction. So the magnesium chloride and silver nitrate inside the test tube or the beaker would be your system, and everything else, including your hand holding it, would be your surroundings. All right, so we're going to look at the definitions for state properties. Okay, it depends only on the state of the system, not the way the system is reached. So the state of the system, there's going to be 4 properties that describe or help defend or support, let me say, this definition. What's important here, one of them is temperature change. That's a state property. Temperature is a state property. And I use this slide to indicate to you that when you see this triangle, it's really meant to be a delta symbol in the Greek alphabet. So delta T equals TF minus TI. So for the purpose of this course, when you see a triangle something, that means you're going to take whatever that is, in this case temperature final minus temperature initial. Temperature final is the ending temperature, and temperature initial is what the temperature was when the reaction began. So what the reaction is at the end, temperature of the reaction at the end versus temperature of the reaction at the beginning. So final is in, initial is beginning, or at the start. This here, change in, is to remind you that that's what the delta means. Okay, so there are the 4 state properties: composition, what it's made of, temperature, pressure, and volume. So now we're going on to the top of page 3. So direction of heat flow, there are some terms to define there. Q, remember, means heat or heat flow. A positive Q means heat is flowing into the system from the surroundings. So heat is flowing into the system from the surroundings. A negative Q means heat flows out of the system into the surroundings. So if it feels warm to the touch, so you're holding a test tube or a beaker, okay, and it feels warm, that means heat's flowing out of the system, whatever's going inside of the test tube or the beaker, into your hand. That's how you have the sensation of it being warm. So that's going to be negative Q, okay? If it felt cool to the touch when you're holding it, we can produce those kind of reactions. Cool to the touch, that means that heat is flowing into the system rather out. So it feels hot to the touch, it's a negative Q. Feels cool to the touch, it's a positive Q. Endothermic reaction, excuse me. Endothermic reaction will be indicated because you will have that cool touch, a Q greater than 0, or a positive value for Q or heat. Exothermic reaction, right, is when your Q is less than 0 or a negative value. Remember that we're talking about heat going in or out, okay? So just consider that when I'm discussing the word Q, or I mention the word Q. So here we have a reaction, methane plus oxygen making carbon dioxide and water, and we have heat. So this reaction would have a positive Q value because heat is given off in the reaction, right? This is a product, it's given off. Here we have potential energy, and we're just going to make this an arbitrary scale. We'll just say 0 to 1,000. That's just me picking up a random number, but it's increasing, right? And so this is an example of an energy diagram, and we're going to draw these later on in the unit. But for now, I just want you to see that this would be a representative of an exothermic reaction, or an energy diagram representing an exothermic reaction. And these things here in blue are what you're adding to your notes on the top of page 3, or about in the middle of page 3. So it says exothermic reaction is the lowering of potential energy. So let's look at this. So if we think about this being our bottom scale to the top, the reactant potential energy is large, right? And the product potential energy is tiny. So here we have the potential energy of the products, this amount here, let's just call this 0 to 100 for ease of purpose of looking at numbers, right? Is less than the potential energy of the reactants, which is 0 to maybe 600, okay? More energy is released to form products than the energy absorbed to break reactants. So I have to absorb energy to break these reactants, right? So it takes a lot of that to happen. And then I've got to form my products, okay? And it says more energy is released to form products than the energy absorbed to break the reactants, okay? All right, so these 3 are your bullets, and I drew this door because what I'm going to show you later is that, think of this as a high-rise, right? An exothermic reaction, your energy diagram looks like it's going out the door of the high-rise. So I think of this as a high-rise, an exothermic exiting the building, okay? So you see your products down here. Okay, so again, exothermic reaction is the lowering of potential energy. So potential energy went from this to this. And I have potential energy of the products is less than, right? So that's this much, than the potential energy of the reactants, pardon me. More energy released to form products than the energy absorbed to break reactants. So it takes more energy to form the products than it does to break these reactants. It takes more to form the products than it does to break the reactants. All right, going on to the next energy diagram. This is an endothermic, oops, still exo, let me go on. Pardon me, this is an endothermic reaction, right? So still we have that very similar diagram, a little bit of different reaction, but this time notice that I have heat on the reactant side. So this is going to be endothermic. So let's look at the diagram again. Endothermic reaction, heat into the system is used to increase potential energy. So this is how much potential energy of the reactants, and this is how much potential energy of the products. So the potential energy of the products is greater because this amount, oops, fix that. This amount of potential energy is much greater than this amount. So let's say this is 50 and this is 300, just for arbitrary value of looking at those. And then the final thing for your bullet is more energy absorbed to break reactants than the energy released to form products. So it takes more energy to break reactants here, where when we look back at that one would have done. Where we look back at a exothermic reaction, it takes more energy to form products. So those 3 bullets you put in your energy diagram. We'll look at energy diagrams in a lot more detail coming up in a few weeks here, or weeks, maybe days, whatever. Okay, so then we're going to go ahead and flip to page 4, and we're going to just make a sketch. This is a very rough sketch, but I wanted you to see, or to sort of build this thing where the surroundings would be your beaker, your flask, your test tube, your hand if you're holding the reaction, the test tube holder if that's holding the reaction, and your system is what's going on here. So if it goes from the system out to the surrounding, it's exothermic, it's going to feel hot. Q is going to be negative or less than 0. If I have a situation where it's an endothermic reaction, so here's my reaction in here and all this stuff is surrounding it, it's going to be endothermic if it's cold, or if Q is positive or greater than 0, you'll see that heat is going into the system, which is opposite of an exothermic reaction. Okay, the next item of business is that I need you to make a formula card. You will not get to use this per se. That's not true. You will get to use a version of this on a test or a quiz. So thermochemistry formulas, I would make a formula page or a formula card where only thing that's on here are the things I'm about to tell you to put on there. That way it's kind of all grouped together and you can quickly access what you need for different calculations. So I'm going to pause and let you, I'm going to raise this up just a little bit. I'm going to pause and let you copy these down. All of these will be given to you on a test or a quiz. So please take a moment to pause the video and write these down. Just to be sure that you understand what these different variables stand for, this is energy, E is energy, Q is heat, W is work, P is pressure, V is volume, so heat, mass, C is specific heat, T is temperature, and then this is a specific heat of water, okay, and this is going to be joules over grams times degrees Celsius, or joules over grams times Kelvin. 1 liter atmosphere, so there's 2 units, equals 101.3 joules. Okay, so 1 liter atmosphere equals 101.3 joules. You're going to also add these conversions to your formula page. These are all pressure conversions. So I can set any of these equal in a ratio to each other. So one on top, one on the bottom, in any way I need to convert units. Same thing with these three. I expect that you know this one. 1 milliliter equals a centimeter cubed, and I would expect that you know 1 liter equals 1,000 milliliters. I won't give those to you. And I do not believe I'm going to give you 1 kilojoules to joules, not sure. I will give you the pressures. Pardon me. Okay, some more formulas to add to your page. I'm going to raise these up a little bit if I can get my computer to cooperate. There you go. So Q reaction, it's important you put Rxn with this, equals negative mass times C times delta T. Q reaction is equal in magnitude, we'll learn about that in a moment, but opposite in sign to Q calorimeter. The Cal means calorimeter. Okay, Q reaction equals negative, this is a capital C, so that's bomb calorimeter, where when we had the lowercase c, oops, we can do it from here. This lowercase c right here is specific heat. So if it's a capital C, it's bomb calorimeter. If it's a lowercase c, it stands for specific heat. And then the change energy of the H, enthalpy is equal to delta H is equal to H products minus H reactants. We're going to use these formulas as we do calculations in this unit. Okay, so hopefully you have all those pages of items written down into what I call a formula page. The next thing I'm going to show you, these are things that will not be given to you on a test or a quiz, but it's worth writing down in your card as a reference so you start to memorize it and start to get familiar with it, and then you're not searching for it in your notes. So if you have a positive Q, remember that means heat is absorbed and it's endothermic. If you have a negative Q, that means heat is released, feels hot, exothermic. If you have a positive W, work is done on the system, or the system is compressed. Okay. If you have a negative work, your work is done on the surroundings, or it expands. Now, it's really hard to remember the plus W and the negative W, in my opinion. So I like to say it's negative to expand your waistband. It's negative to expand your waistband. So when work is negative, it expanded, or if it expanded, then work is negative. Just a little mnemonic device or trick to help you remember that. Okay, we're in the middle of page 4. Please copy down the definition for internal energy. All right, so thermodynamic quantities. This is important for when we use numbers and report numbers. Thermodynamic quantities, or values, are going to have a number, which indicates its magnitude or its amount, and it's going to need a sign, a positive or a negative sign, so we can understand direction of flow. Okay, so you always will include, when you're putting in thermodynamic quantities, a number and a plus or minus to represent the direction of flow. So our first calculation here is going to be calculation 1 in your notes. It says calculate delta E for the system undergoing an exothermic process in which 15.6 kilojoules of heat flow and where 1.4 kilojoules of work is done on the system. You will be required to earn credit to show a basic formula, okay, and then numbers with units plugged in and solve. So you will be expected to show the basic formula and then substitution and solving. Okay, so let's look and think about what we have. We have energy, we have heat flow, and we have work. Okay, so we have Q, and we have W or need W, and we have E. So we have E or need E, we have Q or need Q, we have work or need work. So if you think about it, if you look at your formula page, the one that has all three of those is energy is equal to heat plus work. Okay, so we're going to calculate delta E. Our Q is 15.6 kilojoules, and our work is 1.4 kilojoules. Before I can add anything, it has to have the same unit. Before I can add or subtract units, they have to be the same, or I can't do that. They are the same, so I can do that. Pardon me. And before I can go on, I have to indicate the direction. So I did not do that because I have no plus or minus written by these numbers. It says it's endothermic process, so I know that means the Q is endothermic, it's positive, and it says work is done on the system. So we're going to go back and look at what that means for work being done on the system. So if work is done on the system, it's positive, okay? Work done on the system is positive. Pardon me. So I'm going to indicate that by putting a positive here. So we're going to add these up. Let me grab my calculator. 15 plus 6 plus 1.4. And we're going to just, for this, because we're not doing sig figs this year, and if we are doing sig figs, you'd want to apply sig figs. But if we're not doing sig figs, this would be, if we were doing sig figs, this would be 17.0 kilojoules. For the purposes of this course this year, we're not doing sig figs, so we're going to call it 17.00 kilojoules. And not only can I just put 17, I want to indicate that it is positive. Yes, I realize it's positive because we put no negative there, but we need to be in a good habit of putting positives and negatives in whenever we use or report a thermodynamic value or quantity. Okay, in the next couple slides, I'm going to show you how a formula is derived or obtained from multiple concepts in chemistry and physics. So this is just really for you to watch and observe more than anything. So what we're going to do is I'm going to work on showing you how we get to W equals negative P delta V. Okay, so here we have 1 liter of gas from some kind of reaction, and it expands to 3 liters of gas. So we compress the piston or release the piston, and we have a change in volume. So in this case, we expand the gas by releasing the piston, and it expands up. Okay? All right, so here is my attempt at explaining this. So here is my drawing or rendering of such a thing. So here we have, okay, so back with you. Sorry about that. I wanted to make this so you could see the whole thing. So here we have the initial state. So this black squiggly represents the gas that you saw on the initial previous page in green. So initial state, and then we have pressure pushing down. Okay, pressure equals force times area. And then we have a change in height, right? Two-dimensionally, we have a change in height. If you just think of it to the final state, still have pressure pushing down, force over area, right? But we need to understand that this change in height really isn't a change in height, meaning it goes from 15 centimeters to 50 centimeters. Really, it's really a change in volume. And a change in volume of cylinder is equal to area times change in height. Okay, so P is pressure, A is area, F is force, H is distance. Okay, so looking at that then, we have really a change in volume. It looks here two-dimensionally like we have a change in height. The height of the piston has changed, but really what has happened is the change in volume has occurred. Okay, so I'm going to go back to full screen here, I think. We'll see how that looks. Maybe. Okay, so here we have that same image. I just clipped it over. We're going to then rearrange pressure, in both cases, to solve for force, because force is something we can get to, because force has a relationship to work. So we're going to take P equals F over A, and we're going to algebraically rearrange and solve for force. I did that by multiplying A by both sides. So take pressure equals force over area, multiply both sides by A, and you get force equals pressure times area. Okay, so we know from previous information that work is force times distance. So I'm going to substitute in for F what we know force to be in this example. So where we see force, I'm going to substitute in pressure times area. So now we have a formula that is work equals pressure times area times distance. And we know the distance that the piston changed was a change in height. Okay, so we know then work equals pressure times area times change in height. Remember, distance is change in height, which is the same thing as saying work equals pressure times change in volume, because we learned right here that really the change in volume is the change in area times the change in height, or area times change in height, pardon me, area times change in height. Okay, work and P delta V are opposite signs because when a gas expands, work flows into the surroundings, so work is W. So that's why we have that W, the negative symbol next to W. So W equals negative P delta V. All right, so that is how we go from understanding compressing or expanding gases and the physics of that, and how we can substitute in and derive our formula that we get here that works equal to negative P delta V.